And we're going to talk about data transformation. This is a little bit more complicated um, concept or um, part, a little bit more complicated part of statistics. And to be honest, I didn't know how to do data transformation when I was a grad student. That doesn't mean that you you can you don't need to know, but it's good that you will know through the course, and then you won't feel intimidated by it. Hopefully, because I think even when I think the first second year as a faculty, um, I when they talked about data transformation, I was like, no, I don't know how to do that. That's scary. That's unfamiliar territory, and just felt very insecure when they talked about that. But I, but after having gone through it a few times and then studied it, now I feel like, okay, if the assumptions doesn't meet violation, I'll just look for data transformation. It gives me a way out, or it doesn't make assumption issue like a dead end. So hopefully by the end of today, you'll feel a bit more comfortable with data transformation. So want to recap in terms of last week before the exam. We analyzed, or we looked at the assumption of this dental data set. I don't know if you still remember. It's a long time ago. It's a week and with the midterm exam in between. Sometimes memory might be a little bit foggy. But we had this data set, and we had different variables. The outcome variable was strength, the bonding strength of, let's say, a crown or something on one's teeth. And then there's periodontal dressing, different dressings that they use to put things together, put things on your tooth. And then number of hours, and how after how many hours after the application is the strength measured. So there were these two IVs and this DV. And then we examined normality, homogeneity of variance, and outliers. I don't know if you still remember this. Yeah. Okay. So the reason I'm saying this is because data transformation is related to assumptions. So it is mostly in the context of when assumptions are violated, we go to data transformation to deal with fixing the assumption issue. So in terms of that assumption analysis, we looked at normality, and all of the normality, skewness, kurtosis were within -2 and 2, with the exception of the zone 3 cell. So zone is the dressing, 3 is a 3 hour. So there's 10 different cells because there's 2 levels in one variable, 5 levels in the other. And the zone 3 cell had a larger skewness and larger kurtosis. And however, but we were able to say that because the degrees of freedom was over 20, equal sample size, two-sided, two-tailed, so it's robust under normality. So we didn't really, weren't really bothered by this validation. And then we also looked at the homogeneity of variances. So we split the data up. We found the largest variance, which is 51,606, and the smallest variance was 1,400, and the ratio F max was 36. So this 36 exceeded the 10 ratio, so there was a violation for homogeneity of variance. So this would be an issue that we would have to deal with if we were dealing with a real data set. And then outliers, there were no outliers. So this is some background information recap of what we did. And so today I'm going to talk about transformation, and then start with giving you a graphic sense of what the different distributions look like when they're skewed, and what kind of transformations might work best for these situations. So here's 6 different graphs or distributions. So a normal distribution would look like this, and this would be a positively skewed distribution. And this would be more extreme, substantial positively skewed, and this would be like pretty severely positively skewed. So these are the different extremes of how it's positively skewed. And this would be a negatively skewed distribution, and this is a more substantial negatively skewed distribution, and an extreme negatively skewed distribution. So what the transformation of data is going to do is to make this data look more like a bell curve, look more closer to a normal distribution. That's one of the goals of it. And so there's different types of transforming. One is called square root. So we simply square root that variable, and we'll get a new set of a new variable with a new set of numbers.
So I get the idea of transformation of the variables is to get it so that you can then run statistical analysis.
Yes.
But I've always had a problem with that because it feels unnormal.
Okay, yeah, so you're changing data.
You're changing the data. It's like taking outliers, just like erasing them from the
Yeah.
data. And I'm like, well, but hang on, that was a part of the data set.
Yeah.
So how, is this like an algebra where you have the equal sign and you add like 6 to both sides
Yeah.
and therefore
You add 6 to one side, not both sides.
that changes
So it's
the
not
numbers?
Yes, yes. So, but, okay, if I said, okay, as a class, I'll give you 10 points each, does that change? It will probably change your, like, where you're at in terms of A and B, but it doesn't change your rankings.
For this class, because we're all smart and I love everybody here, correct, it would change A for B, but if you had like someone who's pass or not pass, then that makes the difference.
More people pass, right?
Yeah, so that does make a difference. That is a significant change between you have to retake the class versus
Yes.
you don't. So
Yes.
that's where I'm like,
Okay, yeah, so I think there are certain things that we should be very cautious if we transform the data, certain things that are less important. So for example, if we transform the data, we add 6 points to everyone's back depression score, then we can use the cutoff score, like what we did before, right? That would skew it, like people who weren't depressed would now become clinically depressed. So that would be a violation, that would impact results. But if we're looking at whether treatment group versus control group, which group has, are there mean differences between their depression scores, then we're doing group comparisons. So the scaling of the scores will not matter as much if we like added 6 for each, sort of doing that kind of manipulation. But there's different kinds of transformation. There's this adding a certain number, square rooting, that doesn't change the rank order. But if you inverse it, the largest will become the smallest. The smallest will become the largest. So then when we interpret the data results, we would have to say now smaller scores, lower scores on Beck depression inventory mean after the transformation means higher levels of depression. So we'll have to do a flip in that case. So based on how we are transforming the data, there are certain things that we would need to adjust when we interpret the results. Does that make sense?
yes.
Okay, yeah, and I think those are good questions. And so best practice, best scenario is this. Okay, assumptions, it's violated. So what does that mean? That means if we run the ANOVA, we cannot fully trust the results because the results or the way ANOVA works are based on those assumptions. If they're violated, then we're not sure if the significant p-value is really significant or it's or the error has been inflated and it looks like significant, but actually it's not. So what we do is we transform the data so the new set of numbers, it meets the assumptions. So we no longer have an assumption violation. And then we run the ANOVA again with this transformed data set. And after we get the results, okay, we look to see if it's significant. And then we compare it with the results ran with the original data set. And if the significant level or significant p-value were the same, it would give us confidence that, okay, the original analysis despite it not meeting the assumptions, the results came out identical or the same as the results that we used with the transform data.
Now that's
That-
satisfying,
yes,
what you just described,
yes.
that's a satisfying.
So that would be the
Okay.
best scenario. We would say
Okay.
we ran it both ways, the results were identical, so now we can go back to the original data numbers, because that would be easier to explain.
Okay.
And then, yeah. But the challenging part is like, okay, if one was significant, the other wasn't, so what would we do there? So, I think to be ethical, I think we would have to honestly present, what we found. And then, we could let the reviewers judge, the readers judge, because sometimes things don't come out clean and clear, with real life data sets. But I think the ethical part is, regardless of what kind of manipulation we do, we state it clearly, so that someone could replicate, that if they had a data set. And so that it's not like we're doing something behind closed doors, and then here are the results. So I think that would be, the main ethical part.
Is,
Good question.
is the thought behind research that it should be something that can be replicated by others? And if it's not, then there's something unethical going on?
The thought process is when we write up our manuscript, we should write it up clear enough so others can replicate our study. So, results don't always, the replications don't always come up with the same, results. Like with a different sample, they might have a different finding. But we need to write it up clear enough, so if someone wanted to replicate, they knew what steps we did, what kind of modification we took, what kind of adjustments, we made. So, yeah, so that's sort of, I think that's now, you get a clear sense of why we're doing data transformation, and in terms of the best practices of how to deal with this. And so next I'm going to talk about just the technical aspects of what we do. How do we transform data? It's going to sound intimidating. Square root, that itself is hard to calculate. I can't calculate it in my mind. Logarithm, I think I learned it in middle school or high school, but totally, to be honest, I forget. I forgot what it is, but I know it's called logarithm. And I know how to do it in SPSS. And then also inverse, that's easier. That's putting the x value or the variable that we're wanting to transform in the denominator. So that part I know in and out of what's happening, but not all of it I know. So it feels intimidating, but I'll try to go through it so that at least we know how to run and what to do, the technical aspects of it. Say, okay, positively skewed, negatively skewed, what's going on here. Based on this is like a reflection, right? I don't know if you like to take selfies or not, but if you take a selfie like this, like with the camera flipped, versus if you stand in front of the mirror and like take a selfie there, they'll look different, right? If you use the mirror to take a selfie, you're flipped horizontally. You're just like this pig. Okay, this side becomes this side. So this is reflection. So I'm going to talk about so when we deal with negatively skewed distributions, what we do is we reflect the data. So it's not, here we reflect an image, but in statistical world, or what we're doing, we're reflecting the scores, the values. So in other words, reflecting is kind of like recoding when you're dealing with a reverse varied item. So for example, if we're doing effect depression inventory, we have I feel sad, I have thoughts about hurting myself, and then an item like I feel really optimistic. So of course, obviously that's a reverse item. And so when we score the BDI score, what we would want to do, depression score, is we want to recode it. So if they picked a 4, I strongly agree on that, I feel very optimistic. We want to turn that into a 1, the smallest value. So that's similar to the idea of reflecting. Does that make sense? Okay. So we'll talk about reflecting as one of the 6 approaches when we do data transformation. So this is a set of different ways to do data transformation. And one is to square root, one is to do the log, one is to do the inverse. And if we're dealing with negative skewness, we would first reflect and then do the square root. And or first reflect and do the log, first reflect and do the inverse. So the reflect process is to pick a value, k. The k is usually equals the largest score plus 1, and then use k to minus the score to get the new score. Okay, and I'll demonstrate that with you. And there's also another issue that we need to pay attention to, is that whether there are zeros in this variable. So if they're not all positive, then we need to make them all positive. We don't want a 0 in there, because if we do like an inverse, if there's a 0, a denominator can't be a 0. So to make them all 0 without changing the order of it, what we would do is we would add a c, a value to all the scores, so that the smallest score now becomes 1. So for example, if the smallest score was negative 44, what would c be? 45, yeah, so we would add 45 to all the variables, and then so that all the values, and then so the new, in the new variable, the smallest would be 1. Okay, so these are the technical aspects of the transformation process. So how to determine c and k? If we need to determine c because we want to avoid zeros. So the goal is to make the smallest score of the new variable into 1. And so by adding c to all the cases, or subtracting k from all the cases. So c, how we determine c, is the most negative score. It's absolute value plus 1. So negative 34, the c would be 35. So k is the largest score plus 1. So if we had like a variable that the largest score was 45, so k would be 46. We would use 46 minus the variable. Okay, and then here are some tips of what we would do when we transform data. We would usually just use one transformation, try the chi-square, and then another. If it doesn't work, we just move on to the log. If it doesn't work, we move on to the inverse. If it doesn't work, we move on to reflect, square root. Did I say chi-square? Mm-hmm. Okay, it actually is square root. Sorry. So square root, log, inverse, and then reflect, square root, reflect, log, reflect, inverse. So we would just try one at a time, or and then until we find the transformation that no longer that the data no longer violates the assumption. And if we're unable to solve this through transformation, which sometimes might happen, another way of dealing with it is to dichotomize the variable. So dichotomize meaning if we dichotomize it, it then becomes a categorical. So we're no longer running ANOVAs. We'll run a chi-square with it to it first instead. And so that's another way. So it's not the end of the world if transformation doesn't work. Dichotomizing the variable could also be an option, the second line of option. And then one thing to remember what we talked about is when we reflect or invert a variable, we make sure to reverse the direction of interpretation. So no longer higher scores meaning higher levels, higher scores mean low levels.